This time, let's take a look at how to perform optimal design in 3D in a non-parametric way. The most fundamental method is to first create a generative model using the 3D data you have and then apply it to the generative model. Then you run simulations on the generated models, accumulating data by simulating the generated cases. After that, based on this, since we've generated X and collected Y data here, we can use deep learning to train the function y fx. After training, we use that as the basis for optimal design. Once we've performed optimal design and found a good design, we run an actual simulation on that design again to verify the results. So the good values are fed back into the data set, and then we generate new data using that data set again. We retrain on the new y values, and this process is repeated iteratively. For example, it's not always necessary to have a predictive AI model. If I have design option A and design option B, I can simply interpolate between the two to create a variety of designs. After enabling the generation of even non-parametric designs, I connect this to the CA solver, linking it to the CA solver. You can generate and check the results in real time to create an optimized design. The same applies to CFD. Normally, if you have this kind of input and run a simulation, you can calculate the pressure field as shown here. But now, since AI can predict the field, you find that the AI prediction is almost identical. This means you can also generate 3D models. And as you generate them, you can find the most optimized palette front, especially in multi-object problems. And if you find a design you like, you can use stable diffusion to render it in real time. Now for the last part, let's look at machine learning-based topology optimization. There have been a lot of attempts to incorporate AI into topology optimization. So many papers have been published on this topic, and we even wrote a review paper ourselves. Today, based on that review paper, I'll briefly introduce the perspectives on how AI has been applied to topology optimization. The first idea is acceleration. Originally, topology optimization requires many iterations to reach the final design, which takes a lot of time. So after running topology optimization up to a certain intermediate stage and reaching a certain level of convergence, you train the AI to go from that converged state to the final design. So there is research where the earlier stages are done with topology optimization, TO, and only the final stage is accelerated using AI. The second approach is to train the model in a completely end-to-end manner, without any iterations. So by simply converting the design domain and certain boundary conditions into images and feeding them as input, the final design can be generated directly through deep learning. The third approach is to simply use AI as a meta model. By using deep learning, you can perform FEM to calculate compliance, and based on that, you can also carry out optimal design using the same SIMP method. Next, there's dimensional reduction. If the topology optimization space you want to work with is large, you can reduce its dimensionality first and then perform topology optimization in the reduced space. And there are ways to further improve the optimizer. So thank you for gradient-based methods. We used optimization, but this is a method where if we input a specific coordinate, the model learns to predict the most optimized density value for that coordinate. Next, this can be applied to generative design. It's not just about finding the optimal design, but by combining topology optimization and deep learning, we can find a variety of design solutions. Lastly, it can be used for post-processing. If the design produced by topology optimization has a very rough surface, as you can see, for example, this specific approach utilizes a support vector machine. If you train a support vector machine to effectively differentiate and distinguish between the inside and outside of a certain surface using this data, the resulting prediction generated by the model will come out looking very smooth and consistent. However, topology optimization methods based on machine learning still have quite a few limitations. First, the main issue is computational complexity. Since you have to collect all the data and train the model, the burden of data collection becomes too great. There's also the question of whether it's meaningful to gather and train on such a large amount of topology optimization data when you could just perform optimal design or topology optimization once anyway. And the reason for that is because performing PhA during topology optimization takes too much time. So these days, there's a movement to combine a small amount of data with the physics we already know. Next, the biggest problem is scalability. While 2D problems like the bracket example work well, 3D design and higher dimensional problems do not perform as well. Also, it's difficult to apply a variety of boundary conditions. It's easy to generate for fixed boundary conditions, but when the boundary conditions change, it's hard to generalize, and the quality isn't yet sufficient for practical use in industry. Next, there are issues like connectivity, feasibility, and robustness. When you generate designs using topology optimization, connectivity is still guaranteed because the compliance needs to be good when analyzed. But with AI-generated designs, they might look fine from a distance, but up close you can see that they can be disconnected. Pixels can become disconnected, and if that happens, the performance will drop significantly. So you can't guarantee that kind of connectivity. And it's also not easy to control manufacturing feasibility. Plus, since the designs are generated, the performance can't be robust. You get some good designs, but you also get bad ones.